Hello, everyone. Here I'm going to talk about our paper that is end-to-end evaluation of federated learning and split learning for Internet of Things. This is collaborated by CyberCRC in Australia, Data61 in Australia, and the Soonwon University in South Korea. So we are familiar with the centralized machine learning. In this case, the data is collected by the server, and then the server will train the model. However, by collecting data to one place, this raises the concern of data privacy, because for many business sectors, such as the bank and hospital, they are unwilling to share data with other organizations. And currently, there are also general data protection regulation issued by different countries. This one is actually issued by Europe. One alternative is to decentralized machine learning or distributed machine learning. In this case, the data is resided at the user side, and the data is not seen by server because it is not allowed to be accessed by the server. The server just coordinates different users to train the model. There are several benefits. First is that data privacy concern is greatly reduced. And second is that the model accuracy trained in this decentralized machine learning is still good because the server can still harvest rich data contributed by different users. There are two decentralized machine learning investigated in this work. The first is the most popular federated learning, and the second is split learning or split neural network. This one is proposed by MIT researchers in 2018. Firstly, for the federated learning, the server issues a global model and sends the model to the client. Each client receives the model and trains the model over the data held by each client. After that, the client will update the local model to the server. The server will upgrade these models and do using some algorithm to update the global model. To this end, when run is finished, there will be many runs to have a good model that has high accuracy. So we can see that now the server does not need to access the localized data, which actually protects the user privacy. For the split learning, as we can see here, the whole network is split into two parts. One is the client part, and the other is the server part or the server network. So one client starts the forward propagation on the client-side network and pass the activation from the client network to the server. The server will continue the forward propagation and then perform the back propagation and pass the gradient to the client. The client continues the back propagation. Once all the data in the client is iterated, the subnetwork in the client side will pass to the next client. And this will go through all clients. To this end, one run is finished. Similarly, many runs will continue until the model has a good accuracy. So for the federated learning, the entire model is trained by the client, and the client accesses the entire model architecture. The client trains the model in parallel. For the federated learning, it is applicable to any model architecture, including convolutional neural network, recurrent neural network, and the long short-term memory. For the split learning, only the subnetwork is trained by the client. The client does not need to have knowledge of the other network part that is held by the server. The client trains the model sequentially Currently, one limitation of the split learning is that it is only applicable to vertically splittable model architecture. In particular, it is only applicable to convolutional neural networks. For the IoT device, it can be generally classified into two categories. First is high-end IoT device, and the second is low-end IoT device. The first category had some devices such as the smartphone, Raspberry Pi, and for the low-end IoT devices, they could be RFID cards, credit cards, and sensors. On one hand, for the IoT device, they generate rich data. On the other hand, these data are usually privacy concerned. For example, the medical measurements and the voice speak by the person. So in this scenario, the distributed machine learning technique is very attractive. For current status, there is a very few empirical evaluations on distributed machine learning training mounted on real IoT devices. Actually, we have seen a number of model inference mounted on real IoT devices. However, these models are trained by a powerful server, and then it is stored in the IoT device. These models are not trained by the IoT device itself. Generally, there are very limited study on training model directly using the IoT devices. Secondly, for the FL and split NN, which one is more suitable for this IoT scenario? There is no any empirical comparisons so far. So we have the following main considerations. Research question 1, what is the learning performance of the federated learning and split NN and realistic IoT applications? For example, to resembling the imbalanced data distribution and non-uniform data distribution. The second is, what is the overhead of the FL and split NN by implementing them on IoT devices? In particular, here we use the Raspberry Pi to assess such as the training time, amount of memory used, amount of power consumed, and communication overhead. In our experiment setting, we use the following dataset: the ECG, that is a medical dataset, and the speech command. For both datasets, they are sequential dataset, and they have information that are private. The model architecture, most of the time, we use 4 convolutional neural network and 2 fully connected network. The total model accuracy here is, this stands for the baseline accuracy that is trained in a centralized manner. For the ECG, it has about 97% accuracy. For the speech command, for short, we call that as SC. It has about 85% model accuracy. In fact, we do train the Cifatan dataset with MobiNet V1 on Raspberry Pi. However, we found it takes too long for both FL and split NN. We also tried ResNet on Cifatan as well. However, it also takes a long time. So that's why we're trying to use a simple model architecture or that has less total parameters as well as sequential data rather than image classification problem by training them on IoT devices. The first experiment, we want to figure out what are the learning performance for the split NN and the federated learning. Or more interestingly, we are more focused on the split NN learning performance because this is less studied in comparison with the federated learning performance. So we have the research question 1 is that what factors or settings affect split learning performance? The factors could be number of clients, non-IIT data distribution, and imbalanced data distribution. Here, the IID means that each client has samples from all classes. Otherwise, it is referred to as non-IID. This is going to resemble the scenario where data is personalized. For example, for a medical center, it only matters the medical records from only one person, not others. The balance means that each client has equal number of samples. Otherwise, we refer that as imbalanced data distribution. This resembles scenario where some sensors are more active and some sensors are less active. Second research question is that which setting will the split NN learning performance outperform the FL? Here we show the setting of the IID and balanced data distribution. This is for the ECG dataset. Here we increase the number of clients from 2 to 100. And this figure shows that the same setting of the IID and balance the data. However, this is for the other dataset, that is the speech command dataset. For this blue line, it shows the federated learning only performs one local update. For the red line, it means that the federated learning has 5 local epochs. Interestingly, we can see that for the split neural network, its training accuracy actually fluctuates a lot. And once it rapidly reaches to the optimized accuracy, it actually slightly drops. So that means in practice, we do not need to setting many runs for split NN. Once it reaches to the optimized accuracy, we can stop that to save time and also save other overheads. Based on the above results, we can conclude that split NN learning performance is affected by the number of clients. Accuracy cannot achieve the same accuracy as centralized learning when number of clients increases. This conclusion is also applicable to the federated learning. For research question 2, we conclude that split neural network always outperforms the FL in terms of convergence speed in our experiments, because as we can see that the split NN usually converges fast, so it can converge within 100 epochs. However, for the federated learning, the convergence speed is quite slow. This setting shows the imbalanced data distribution. And here we see that the split learning had some difficulty when the number of clients increases to 100 and the data is imbalanced distributed. So for the first probably 50 rounds, it does not learn. However, once it starts learning, it rapidly converges. We have the following conclusions based on our experiments. The split NN learning performance is affected by both the number of clients and imbalanced data distribution. The split NN converges faster than FL in our experiments. Here it shows the learning performance under the non-IID data distribution settings. We can see that actually for the split NN, it does not learn at all under some extreme non-IID data distributions. We have the following conclusions. Split NN is very sensitive to non-IID data. In fact, both federated learning and split learning, they have this issue. There are knowledge forgetting when trained on the non-IID settings. The federated learning outperforms split NN and non-IID data setting, especially in the extreme cases, as we already show. So in these cases, the split learning does not learn. That means the split learning, one client has only one class, 2 classes, and 3 classes. The split learning cannot learn in this scenario, in this extreme scenario. The possible reason is that in the approach of model training, FL aggregates the local model strain on the local data present at each client. The aggregated model usually has more knowledge of the data classes, even though there is one class per client. than the cases where the model is sequentially learned over the clients without aggregation, such as in the split NN. In the second experiment, we mount the split learning and the federated learning on the Raspberry Pi. Here, we treated the Raspberry Pi as a gateway. It collects data from the low-end IoT devices and running the training process along with the server. The server basically is a laptop in our setting. This is a picture of our experimental setting. So we have several Raspberry Pi, and on the right side, we have a plug-in power meter to measure the energy consumption. On the left top, we have a Raspberry Pi with fan. This is because we found that during training, the temperature of the Raspberry Pi goes up to be up to 80 degrees. So we can use a fan to cooling it down. Now let's have a look at the demo of our experiment. We have two clients and we have one server. Firstly, we set the number of epochs and the number of users. Then we run the server side. Now we find the IP address of the server, and we input the IP address in the Raspberry Pi. Here we reset the power meter. Now we are ready to train. Here we can see that the first client started training and the server also trains in this scenario. Because this is for split learning and the client will train the model sequentially. So I will skip some. Once client 1 finishes this, the client 2 started training. Here we can also see in the server side, this is about training with the client 2, the other client. Now the training time. We can check the temperature memory usage from here and here. Here we have the communication overhead. And here we have the training accuracy and the loss. Now we read the power consumption. So overall, we have measured the following overhead: running time, memory usage, power consumption, temperature, and the communication overhead. We are more interested in the running time, power consumption, and communication overhead. So firstly, we increase the number of Raspberry Pi, or the number of clients, from 2 to 5. We can see in this scenario, the FL uses much less training time, and the FL had extremely reduced communication overhead. In fact, here we cannot see the FL value because the split NN has much higher communication overhead in comparison with the FL. In this case, we see the split NN has relatively less memory usage. The reason is that the split NN only trains subnet of the entire network, so it uses less memory. Generally, the FL uses less memory. Sorry, the FL uses less energy. This is partly because of the split NN trains sequentially. So that means when among all the clients, only one client is training, but all the other clients, they are waiting. So one solution is that in practice, we could switch off the device that on the waiting state to save energy in the split NN training process. The FL has higher power peak, thus has higher temperature. So this explains we probably need fan to cool the Raspberry Pi in practice. In this scenario, we increase the number of the entire network from 4 to 8. Overall, the overhead of the FL increases, while the split NN remains unchanged. The reason is that because the split NN only trains 2 neural networks, regardless of the number of layers for the entire network. The takeaway of this IoT measurement is that for small DNA model that we use or we tested that are more applicable to the IoT device, the FL is usually preferred because it has much less communication overhead and less training time. And we regard the communication overhead is a big concern in the IoT scenario. Other experimental settings and results can be found in our paper, and our source code has been released at the GitHub. This also includes a guide how to configure Raspberry Pi, because actually we faced with various difficulties by trying to train the model on the Raspberry Pi. And we hope this guide will be helpful to other people. Thanks.